Alright, for this one, let's go ahead and start off with the bar chart, with the LOL bar chart. So we have a bead, and it's starting off at some height, so it starts off with potential energy. And it starts off at rest, so it has all potential and no kinetic. So originally, there is 0 kinetic energy, but there's some maximum value of potential energy. Now it says there is no friction, so without friction, so there's no energy leaving our system, and there's no energy going into our system. And our system consists of the bead and the roller coaster, so pretty much everything in the picture is our system, and there's no friction. Okay, so whenever it gets to point A, at point A, it's at some new height. It's at a smaller height. So it doesn't go back up to its original height. It's a little bit smaller. And that means that energy has to be conserved, and so the difference between those two has to be equal to the kinetic energy at the end. Our goal ultimately is to figure out, well, what is the speed, what's the velocity at point A? Alright, so our bar chart is going to allow us to do our equation. And so that means we're going to start off with the UG original, and that's going to be equal to UG final over here on the right hand side plus the final kinetic energy. And we can go ahead and expand those equations. So this is going to be mass times gravity times the original height. That's going to be equal to mass times gravity times the height at A plus our kinetic energy, which is 1/2 the mass times the velocity at A, what we're looking for, squared. So we should notice pretty quickly here that the mass of the bead doesn't matter. In fact, they just said it was a bead. They didn't even tell us what the mass of the bead was, because mass is going to reduce out. It's going to go away. It'll cancel. So we can go ahead and clean up our equation a little bit. And I'm going to go ahead and move like terms over to the same side. So gravity times the original height minus gravity times the height at A. That will be equal to, what's left on the right side now is just the velocity at A squared, and then we still have the fraction divided by 2. Alright, let's do just a few final steps to clean that up. So we can go ahead and pull the G out. And then we have the original height minus the height at A. Our 2 on the right side that we're dividing by, let's go ahead and multiply that on both sides. So it'll cancel out on the right side, and I'll have 2G delta H, 2G times the change in height, and that will be equal to the velocity at A, what we're looking for, squared. Which means to find the velocity at A, we're just going to take the square root. And it's going to be the square root of 2 times gravity times the change in height. The original height minus the height at A. Okay, so we're given the original height. The height at A, do not get tricked by this. The height at A is the diameter, and they give you the radius. So our height at A, I don't know why it's not writing. Okay, let's try that again. The height at A is going to be 2 times the radius, which my number would be 14. Alright, so let me plug in my numbers. The velocity at A for me is going to be the square root of 2 times 9.8 times 21.6 minus 14. So my answer, the velocity at A for me is going to come out to 12.20 meters per second. Alright, so your answer should be something similar. There you go.